So in this clip, we're going to do two short exercises for computing volume of spheres. So for the first one, we're going to integrate over r 4 minus x squared minus y squared, square rooted, with respect to area. And here r is going to be x squared plus y squared less than or equal to 4, and obviously greater than or equal to 0 because they're non-negative terms. And we'll just take the ones with x coordinate strictly positive. So that gives us the positive half circle right here of radius 2. So that's going to be our domain of integration. And so let's see. So this so once again we can think of this as a function of x squared plus y squared, and we see that the domain also looks a lot like circles and radial lines. I mean, in other words, the boundaries of this region are given by circles and radial lines. So if we start from the center and then we proceed outward on a radial line until we hit this curve here, then we can see that the bounding curves for this integration are, we go from radius equals 0 to radius equal 2, and then we're going to go from theta equals minus pi over 2 to theta equals pi over 2. And our integrand becomes square root of 4 minus r squared. And then we have our r dr d theta. Don't forget your Jacobian. And okay, so then let's see. So this is an integral over a rectangle, and there's no thetas in view, so we can split this apart into the d theta integral and the r integral. Oops, that's not a 2. There we go. 4 minus r squared, and we've got an r dr. So this is perfect for doing a u substitution, and when you do that u substitution with u equals 4 minus r squared, du is going to be minus 2r dr. Then this boils down. Let's see. So for the first part, we're going to get theta evaluated all the way across there is going to just be, that's pi's worth of theta. And then from the other one, we end up with minus 1/2 times 2/3 4 minus r squared to the 3/2 integrated from 0 to 2. And so that's pi times 8/3. So 8/3 pi. There you go. There is our answer. So let's look at another example. This time we're going to look for the volume inside the sphere x squared plus y squared plus z squared equals 16. And we want it to be outside the cylinder x squared plus y squared equals 4. All right, so what's going on now? Well, if we look at this, just the top half of this, it's going to be something like this. And let's see, so we've got a sphere, and we are going to cut out this cylinder right here. So the region that we're interested in is the one that's out here. Okay. So if you imagine what this looks like from above, so here's you up in space looking downward, what you would see is you would see a green annulus that circle cannot survive. It was born bad. Okay. And so this is the region of integration. And so we're going to, in this region, we're going to be integrating from the floor up to the sphere. And we're going to set up this integral so that we're actually going to be integrating over this domain in terms of radial lines. So in other words, we're going to be going from the inner circle to the outer circle. Okay, so the volume is going to be 2 times this is 2 times this one, right? 2 times the double integral over the domain of our function. So we solve this for z 16 minus x squared plus y squared. So that's solving this equation here for z. And then we have this thing, so that's going to be with respect to the area, and so our d in this case is going to be x squared plus y squared traveling between 4 and 16, which is going to be r between 2 and 4. So this becomes 2 times 0 to 2 pi, because we go all the way around that annulus, and then we go from 2 to 4, and then we have square root of 16 minus r squared r dr d theta. And now the hard part's done, and it's just a matter of brute force crunching out those suckers. So once again, there is no theta in here, and we're integrating over a rectangle in the r theta space. So this is just going to come out, the theta integral is just going to be 2 pi. And then we have the integral from 2 to 4 of 16 minus r squared to the 1/2 r dr, and that can be solved with a u substitution. So this is going to be, let's see, we've got 4 pi, and integrating that we'll get minus 1/3 16 minus r squared to the 3/2 evaluated from 2 to 4, which is 4 pi times 4 root 3. So we get 16 pi root 3. Wow, that's about as irrational as it gets. There we go, there's our answer. Before we leave, let me just go over one part again. And that is because students often have a question about this, and that the question is, how do you know where to, or when your radius does not start from 0? Because quite often you see it starting from 0. And the idea is you want to think of that domain. Let me just color it here. You want to think of, like, when you draw a radial line from the origin heading outward into space on some straight line in some direction, where does it first hit this domain, and then where does it leave? That's the thought process for figuring out what the bounds should be for your radius. So if I start at the origin and I head off in some direction, I want to say, okay, what's the curve on which I first enter the region, and then what's the curve on which I exit? And so this is going to be r equals 2 in the inside, and then I leave when I hit this circle, r equals 4 on the outside. And so that's why the integration does not start from 0.